One of the last things we have to talk about regarding SnX, EX kind of reactions, substitutions and eliminations, are the stereochemical consequences. So the first thing we should probably do is just review what stereochemistry is, and it's this idea of being handed. And the most common way that we're going to see this is with a carbon bonded to 4 different things. So let's just pick out just a random looking alkyl halide. So, and we'll set this up such that we're going to kind of very likely get some sort of SN2 reaction. Let's choose a really good nucleophile that doesn't tend to do much else. And what we're going to keep track of is what happens in this SN2 reaction. And if you remember, the one thing that is absolutely necessary of the SN2 is for this carbon to approach the back side of the carbon that has the leaving group on it and kind of punch off this other group right here. And one of the things that I kind of think about happening is that these 3 groups really undergo kind of an umbrella flip, right? And so we say that SN2 occurs with an inversion, and if we were going to keep track of all this, we've got our new nitrile, and then now we have this kind of inverted center right here. Right? And so that umbrella flip is said to occur with inversion of stereochemistry. So that I think is pretty straightforward and pretty easy to understand. The thing that we should mention that if you wanted to produce some sort of synthetic product that overall retains stereochemistry, usually what you do is 2 different inversions. I believe that's called the Walden inversion. So for instance, if you wanted to introduce this group into something that looked like this, and then to retain the stereochemistry, typically you'd introduce like an I- in the first step to do an inversion there, and then introduce the CN-. So ultimately you'd end up with what looks like retention, but it really is proceeding by way of 2 inversions. And I wanted to contrast this with what happens in the case of an SN1. Keep in mind, mechanistically, when an SN1 happens, first of all, we kind of have to change the structure of the substrate a little bit. Let's just do it this way. We'll make it a tertiary center. Let's just say a propyl group. And keep in mind that mechanistically, what happens in an SN1 is that we're just kind of waiting around for that bromine group to leave. And the fact is that that carbocation intermediate ends up destroying whatever chirality you had in the first place. So here, I'll just kind of draw my sp2 hybridized carbon here with its positive charge, right? And so the idea is that that methyl group and that ethyl group are existing in the same plane. So in the second step, when some sort of nucleophile comes in, I don't know, whatever it happens to be, whatever solvent happens to be there, we can now attack from either side, right? And so what happens in an SN1 is that you get about 50% retention and 50% inversion. So in that sense, as we've kind of mentioned a little bit in the last term, SN2s are said to be stereospecific, right? They have very specific stereochemical consequences, whereas SN1s end up just kind of doing anything. And we're not going to talk about a bunch about E1s, but they also are kind of in the same boat, right? Because they go through the same exact intermediate, and then the hydrogen that can be plucked off in basically any way you want. So SN1s and E1s typically don't... You would never do one of those, first of all, for any kind of stereochemical control. And quite honestly, you wouldn't really do one of those on purpose, except for maybe in a mechanistic type question in this class. So the E2s, I think, are probably the most interesting case to look at. So that's what we'll take a look at now. Okay, so one of the things I wanted to mention is that there's a resource guide available that has a whole bunch of different examples of this that I'll post some answers to. And what we're going to be assuming in a question like this is that whatever kind of general nucleophile that I suggest, right, is only going to undergo only going to undergo an E2 reaction, because we already talked about the stereochemical consequences of the SN2. So for a second, let's just imagine that this is our substrate, that we have just some strong enough base that we can actually get an E2 to happen. And what you have to do is make sure that you recognize that an anti-paraplanar arrangement relative to this leaving group has to be true, right? And so what we're going to have to do is we're going to have to take this thing, and we're going to actually take this H and rotate it into the plane of the board by doing a rotation that looks something like that. And what we have to do is make sure, this is at least the easiest way of thinking about these things, is that we end up with that anti-paraplanar arrangement of that beta hydrogen that we're trying to extract, right? And so this kind of arrangement is pretty important. There are some kind of intermolecular looking ones that happen in the plane where Br is, or whatever the leaving group is up here. We're not going to talk about those. Those are pretty specific. But this kind of anti-paraplanar arrangement, you'll notice that when I rotate that H into the plane of the blackboard, that puts this phenyl group back. And then this ethyl group is now pointing out at us. And I'm just going to abbreviate it as an ethyl group like that. And of course, we haven't done anything to this tert-butyl group up here. And now that I've arranged it in a really particular way, you'll notice when that nucleophile comes in and undergoes an arrow push that looks something like that, you'll notice that this ethyl group and that tert-butyl group all end up in the same plane, right? And so, or I should say that ethyl group and the tert-butyl group end up on the same side of the compound. So if I was going to just kind of, draw it in kind of an oddball way, I would draw my double bond that just formed and keep the wedges and dashes as they are. And so you'll see that, right, if I'm going to now take this thing and rotate it into, so that everything is in the plane of the blackboard, you'll notice that the ethyl and the tert-butyl group all end up in the same side. So this is why we consider the E2 reaction, just like the SN2 reaction, a stereospecific reaction. And so all the rest of the examples that are on that sheet, I'd encourage you to give them a try and just make sure that you feel comfortable with doing these kinds of rotations, right? And sometimes you'll have to rotate the leaving group into the plane of the blackboard, and you'll have to rotate the beta hydrogen into the plane of the whiteboard. But in each case, you have to make sure that whatever H you're ripping off, it actually is held in that manner right here. In fact, if I couldn't get into this rearrangement, right, there was some sort of reason that I couldn't rotate about that bond, that's going to severely limit my ability to do the E2 reaction. So give a couple of those a try, and keep in mind how you do the E and Z nomenclature system for these guys. That'll be important on your celebration of knowledge as well. If you have any questions, ask me in office hours.